Okay, so let me give you the statement of the Taylor's theorem with remainder. Okay, so let's suppose f of x has n plus 1 derivatives in an interval I that contains some number a. Okay, then for all x in I, so I is an interval, okay, there is some z also in I, okay, actually scratch that. The z, we can actually make it even better. It's strictly between x and a, okay, where the remainder, okay, remember the remainder that we did, is equal to f sub n plus 1, the nth derivative, taken at z over n plus 1 factorial, okay, times x minus a to the power n plus 1. Okay, so this is giving us sort of an error bound on the Taylor's theorem. All right, let's go ahead. Let's actually do one with this first. So let's approximate the integral from 0 to 1 of sine of x to the fourth dx to 0.0001. Okay, which just out of, that's 1 over 10,000. Okay, so we're going to start by the approximation of sine of x to the fourth. Okay, sine of x to the fourth. Now remember, we have a series representation for sine. Okay, this is the sum, so we don't have to actually calculate all the derivatives. We can do it just directly from sine of x to the fourth. Okay, and it's going to be the same thing as if we had done it with the derivatives. Okay, so sine of x to the fourth is going to be negative 1 to the n, x to the fourth raised to the 2n plus 1 over 2n plus 1 factorial. Okay, where we're using this sine of theta is equal to, we're using the Taylor series for sine of theta at x equals 1. Okay, oop, that should have been theta there. We're just replacing theta with x to the fourth. Okay, so let's integrate this. The integral of sine of x to the fourth dx is equal to, well, there are always some issues with doing this, but we're just going to say it's the sum of the integrals. Let me write that as 8n plus 4 over 2n plus 1 factorial. Okay. Yes, there are, like, if you're really being picky, I should say why. I can just interchange the sum and the integrals, but we're not going to be that picky in Calc 2, okay? But yes, there's some pickiness there. Okay, so let's take the integral term by term. That's going to be negative 1 to the n, x to the 8n plus 5 over 8n plus 5 with 2n plus 1 factorial from 0 to 1. Okay, so that's going to, or that is equal to n goes from 0 to infinity. Negative 1 to the n, and then just that 1 is just 1. So 8n plus 5 over 2n plus 1 factorial. Now, we want this to accuracy 0.0001. Oh my gosh, how many terms are we going to have to take? Oh, I hope not too many. By the way, calculus with trig functions is always done in radians. Okay, if you do it in degrees, then you have to add a factor of pi over 180 to everything. We don't really want to do that. Okay, so let's just do it in radians. Okay, so let's take these terms. Remember the alternating series test? The remainder is less than the next term. So let's take, let's call b sub n 1 over 8n plus 5, 2n plus 1 factorial. Okay, oops. Let's do actually 1 over b sub n. It'll be easier to deal with. 8n plus 5 over 2n, or times 2n plus 1 factorial. Okay, so when n equals 1, I mean, I'm already running out of space. When n equals 1, what are we getting? We're getting 1 over b sub n equals, well, that's going to be what? 13 times, I have it written down, of course. No, I didn't do that one, but 2n plus 1 is going to be 3 factorial times 6. 78. 6 times, yeah, 78. Okay, that's not bigger than 10,000. Let's do n equals 2. B sub 2, that's going to be now 21 times 5 factorial, which that one I did write down. That's 2,520. Oh, wow, we're getting close. N equals 3. N equals 3. That's going to be 1 over b sub 3. Okay, so that equals 29 times 7 factorial. Okay, I'm just going straight from here. So when n equals 3, right, 24 plus 5 is 29. 6 plus 1, 7 factorial. And that is 146,160. Guess what? So our approximation only needs to take the 0, 1, and 2 terms. Okay? This is approximately. N equals 0 is 1/5. N equals 1 is 1 over 78. n equals 2. I've already actually even done these. 1 over 2,520. And that comes out to 0.1876. Okay, see how quickly you got an answer? You didn't really have to do much. I know it feels like a lot, but I mean, you really think about it, your computer would do that in a minute. Not even a minute, that's a long time. Your computer would do that in like a fraction of a second, okay? All right, I'll see you in the next video.